All right, welcome to the last hour. So I wanted to switch, well, not yet quite switch gears. I'm almost done with this current batch of slides, but I wanted to mention now the weak pigeonhole principle, which says there's no injective map, well, essentially from A to A over 2. I made it A plus 1 to A over 2, which is written here, and the only real difference is we're letting y range up to 1/2 a instead of before it was to a, strictly less than a. But we're just saying there's no injective map, no one-to-one map from a set of size a plus 1 to a set of size a over 2. And then we have the same sort of propositional translation just as before. The for all x less than or equal to a turns into a conjunction. The exists y less than or equal to n over 2 turns into a disjunction, and so forth. And we again get a polynomial size formula. I should have mentioned before, how big is this formula? It's supposed to be polynomial size. Well, the size is order n cubed, because I and I prime and j are all ranging over approximately n objects. So it's polynomial sized in n. And the weak pigeonhole principle says it's in some sense more true than the pigeonhole principle, if there's such a notion of more truth, because it's harder to get an injective map from a plus 1 objects into a over 2 objects than it is to get an injective map from a plus 1 objects into only a objects, right? You have to stick an extra a over too many objects someplace that aren't supposed to be there versus only just one extra, right? It's harder to lose track of the counting and so on. So this then translates into the notion that it's easier to prove the weak pigeonhole principle, and that's really more precise. In particular, already Paris-Wilkie-Woods, and then a refined version due to Massiel-Patassian-Woods, shows that these fragments of bounded arithmetic can prove the weak pigeonhole principle. So here again, the second order predicate, the oracle alpha, is encoding the graph, the relation of a function that may be giving an injective map violating the weak pigeonhole principle. And we can prove that T22 of alpha can prove that's not the case, right? That for every number a, alpha is not encoding a one-to-one map from a plus 1 into a over 2 objects. Okay. And correspondingly, by the Paris-Wilkie translation, the tautologies weak pigeonhole principle n plus 1 to n over 2 have polynomial size sequent calculus proofs of sigma prime depth 0. So here sigma prime depth 0 means you have sequence gamma arrows delta, and all formulas are small conjunctions or small disjunctions. Okay, so the sequence could be big, so there could be a lot of formulas here. So essentially a sequent turns into an OR of its members. You can think of this being the gamma implies delta is the same as well, it's the and of the formulas in gamma implies the or of the formulas in delta, and when you can just convert that, when you change the if then into a not or, it's just a big that's a big disjunction, a big or. And so we're taking, the sequent is essentially saying a big OR of things with small fan in. The proof is just complicated enough. I like this proof a lot, but it's just to complicate both versions, the original one of Paris-Wilkie-Woods and also the more recent one. But they're a little too complicated to present here. Tony, who's one of the authors of the second one, is sitting right here. Will speak tomorrow, so come to her talk. But I don't think you'll talk about this, will you? No. So on the other hand, if you go down a level, this is in T22 of alpha. T12 of alpha, and hence S22 of alpha, does not prove this statement. So this is an unconditional statement because think of it just like we can prove unconditional oracle separations. This is an unconditional statement that T1 of alpha can't prove the weak pigeonhole principle. Remember, S22 of alpha is conservative over T1 of alpha, so one of them proves it if only if the other one proves it. So it doesn't matter which theory you're talking about. And so for this, the proof, I guess I can sort of wave my hands over the proof. If S22 of alpha did prove this statement, there should be an of alpha in here, then there would be a p to the NP algorithm which means NP relative to the oracle alpha. So the polynomial time algorithm can query alpha, and also the NP queries themselves. You're calling a non-deterministic query, and that's a non-deterministic Turing machine which can make queries to alpha, which, given the size parameter A and oracle access to alpha, finds a place where alpha fails to be a violation of the pigeonhole principle. Right? Which, okay, a little complicated to say that, but that means there's some place where x and x prime and y are defined that give you an error, or an x for which there is no y for which alpha is defined. The thing is, an algorithm can be, if you had such an algorithm, it runs for polynomial time, it makes polynomial many queries to NP, and we can then build an alpha as an adversarial type of argument that foils that algorithm. And the idea being that as the polynomial time algorithm runs, the adversary forms a partial 1-1 map. And the partial 1-1 map sets some of the values of alpha. And every time an NP query is made, if there's a way to give the non-deterministic query an accepting computation that yields the answer yes to the NP query, that where the answers made to the oracle during that accepting computation are consistent with alpha encoding a 1-1 map, okay, then the adversary sets alpha to include one of those partial 1-1 maps. Okay. So in this way, each yes answer of the oracle query only sets polynomially many more values of the partial 1-1 map. The no answers, there's no way to ever make a partial 1-1 map that turns the answer yes. The algorithm then runs for polynomial time, makes polynomially many queries, sets a polynomial size partial 1-1 map, and at the end, it's unable to produce the needed values, okay, because it doesn't know them. The places where it's queried alpha haven't provided them, so any values it gives can be just violated by the adversary immediately. Okay, this was very hand-wavy. I don't want to do too much more than that, but the point is we can make an oracle type of argument that shows there's no way for S22 of alpha to prove this statement. Yes?
Is there just like a complexity theoretic way of stating this? Like, does this separate P to the NP relativized from something else?
Oh. Well, let's see. I guess we know. So the question would be, does this give an unconditional separation?
Oh, well,
yeah.
Unconditional based on the oracle, right? Like
right.
The way the phrase is completely in terms of.
Well, you could. Okay, so you could. The point is, with queries to a sigma 2 oracle, you could find a way where it violates it. But so I guess this would say this. So this says that at least there's some sort of provable. You can't provably get P to the NP the same as sigma 2. Okay. I haven't thought about that from this point of view. It's a good question. Maybe there's some way you could get more out of this to separate complexity classes.
You could just say that it's not witnessable by PLS.
Say again. Oh, well, the PLS actually is a little bit of a problem here because I think I was saying that, but then to myself, but I wasn't quite sure that's true because we're saying that, see, this is a pi b2 implies sigma b2. So if you make this, we're really looking for either an x where there is no y, or an x prime and a y where this happens. So we're really proving a sigma b2 statement when we're talking about the using the graph alpha form of the pigeonhole principle. So we don't get the PLS theorem for T12 of alpha in that setting. If we came back to this earlier questions about representing the mapping by a function symbol, then we could use PLS, and there's a pretty simple proof there too that can be done. But in the oracle setting, I actually don't see right off how to do that. Okay. Morioka's PhD thesis does it that way, talking about PPP and so forth. Okay. Okay. So we get this separation, and this actually wanted to show this partly because it's nice result, but also because it illustrates the fact that we have a barrier here at T22 of alpha. We're able to give lower bounds we're able to prove the non-existence of proofs in T12 of alpha, but T22 of alpha forms a barrier. So we have a barrier at T22 of alpha. So the word barrier been thrown around a lot for the last maybe 10 years now of a reason we can't prove the theorems we want to prove, right? And a barrier means something that stops us. There's some sort of barrier at T2 of alpha where it's hard to get independence results or non-provability results for T22 of alpha. So we can get them for T12 of alpha. We've got these nice characterizations in terms of PLS or in terms of queries to NP, but we really don't have any good independence results for T2 of alpha. So Pavel's going to tell me one.
No, you should say what complexity, because we do have what's
we do have, well, what complexity? Oh, well, okay, for higher complexity though, right? Yes, yes. So I'm talking about, well, okay. Well, let me, actually this will come on the next slide. So here, think about the for all sigma b0 consequences, the for all sigma b1 consequences. We don't have any good lower bounds for these things here, right? So we know by the bonus theorem I gave you back at the end of the morning session, the first morning session, that T2 of alpha is not equal to T2 of alpha, because if they did, the polynomial time hierarchy would collapse if they were equal, right? But what about lower level complexity? For, think about just the for all sigma b0 consequences, or the sigma b1 definable functions of these theories. We don't have any good way to get combinatorial style lower bounds, like for instance the pigeonhole principle for T22. Emil Jarabek has a theory APC2 of approximate counting, which has logical strength somehow close to T22, although no direct relationship is known between the two things. It's based on an axiomatization using a dual weak pigeonhole principle. Instead of talking about injective functions, it talks about surjective functions. Likewise, APC2 sort of provides a similar barrier. It seems to be the same barrier, APC2, right? I have to mention this open question. The Ramsey theorem is known to be provable in T32 of alpha. Pavel showed this. But it's open whether it's provable in T2 of alpha. It's known to be provable in APC2 by Emil's work. But it would be this is the kind of thing where it'd be nice to try to prove lower bounds for T2 of alpha. It'd be really wonderful if you could prove a lower bound of this for T2 of alpha, because that would be breaking this barrier. But it does mean that so far we've been unable to get good characterizations of the sigma b1 consequences, say, of T22, the way we did for S12 and T12. Other comments or questions here. If you translate this barrier into the setting of constant depth proofs, I hope I haven't been too aggressive on stating this, but I think this is open. Do we have sets of sequence of sigma prime depth 0, which have size S sequent calculus refutations of sigma depth 1, but don't have quasi-polynomial size in S refutations of depth of sigma prime depth 0? I think this is open. Okay. Or more generally, if that's, maybe that is known, but more generally, we don't have a super quasi-polynomial separation of depth k sequent calculus proofs from depth k plus 1, for at least for general k, with respect to even refuting, spelling error there, refuting sets of clauses. So, which is somewhat striking, which is a very strange situation, because we have switching lemmas that tell us that you can express more with depth k plus 1 formulas, AC0 depth k plus 1 formulas, than you can with depth k. So you can express more with these things, but we don't know if we can prove more with these things. So it's a tantalizing thing. It seems like we ought to be able to get these kind of separations. On a related note, Razborov showed that you can get Razborov-Rudish style natural proofs from T12 of alpha lower bounds proofs. And it's not known whether this is possible for T22 of alpha. And Razborov actually speculates this is due to the fact that T22 can do approximate counting, right? So it can prove the weak pigeonhole principle, for instance. And so it's an interesting barrier here, I guess, is what I'm trying to say. So,
Abstract natural proofs, you mean every proof there?
What's sorry?
You mean every proof in T12 alpha of certain logical complexity is a natural?
So, okay, so what is natural? So there's a very technical meaning of the word natural proofs. So here we're talking about natural proofs that things require super polynomial size circuits. And the natural proofs have these things of largeness, constructivity, and usefulness, right? I do not want to get into the definition of that. That's definitely another talk. But the point is, he gets natural proofs from a T12 alpha version, and his proof went through PLS, Karchmer-Vidgerson game for a split version of PLS, You can also get this via other proofs. That, there's a paper of Krychek's and a survey of mine where you instead translate it to resolution and then do the interpolation theorem for resolution. But either one, you can do it either through PLS, the way Rasbroff did it, or you can do it these other methods. So because we have these ways of describing the sigma b1 definable functions of T12, we're able to extract the natural proofs. Okay. Without that, we don't know what to do for T22. Yes, Marco.
Is this a formal barrier? So do you get like very strong consequences if you get a characterization of the definable formulas in T22 alpha?
Right. So the question is this a formal barrier? Not that I know of. I can't make this precise. It's just something that seems to be an operational barrier. But maybe there's something that could be said about this. And there's, see, several people have, so there's a paper of Neil Toppin and Leszek Kolodziejczyk and mine where we address this issue, and I think other related papers as well have sort of looked at this barrier and not been able to get past it. Okay. Okay. Pause. There's the end of the last hour's talk. Other questions before I unpause? Okay. Okay, last chance for deep breath, and then we'll unpause. Were there other questions on the last stuff? Okay, so back to TFNP problems. Keep me on the right time limit here. I'm supposed to end at 5:30, right? Yes, okay. So a TFNP problem. Here's a redefinition of TFNP. It's the same as before. So a total NP search problem, it's given by a polynomial time relation R of xy, so that R is total. For every x, there's a y such that R of xy. And it's honest, which has, i.e. has polynomial growth rate, so if R of xy holds, then the length of y is bounded by a polynomial of the length of x. And the TFNP problem is given an input x, output some y, such that R of xy holds. This class is intermediate between P and NP. It's sort of related to NP intersect co-NP, but okay, I don't want to get into that for this talk. It's easy, but a side channel. And where have we seen TFNP problems so far in my lectures? Two places. One is in PLS problems. I already said that was a kind of TFNP problem. And the other was, well, why is it not on my slides? Well, there it is. 5 slides in, just read the top line only. Sigma b1 definable functions of bounded arithmetic give rise to TFNP problems. Back. Okay. So again, when we have a sigma b1 definable function, then we get a TFNP problem because we're saying there exists some y satisfying some sigma b1 property, so the y plus the witness that the sigma b1 property is true always exists, and it's polynomial time recognizable, and so it's a TFNP problem. Okay, good. Questions on this? Let's start with the easy stuff. How many people have seen TFNP before? Very good. Okay, about half of you. Okay. So a crucial definition for us is the notion of many-one reduction. We have 2 TFNP problems, R and Q, and we want to say that R can be solved if we have a method of solving Q. So this is what a notion of a many-one reduction means. Many-one means that we can solve R by just making one query to Q. Okay? So the many-one reduction from R to Q is a pair of polynomial time functions f and g such that for any input x, think of this as an input to R. So we're looking for a y such that R of xy holds. If we have a y which is a solution of q of f of xy, then the function g gives a solution to R. So again, we're given input R. We want to find some value such that R of x and that value holds. We compute f, and we get to ask one question to q. And we ask q of f of x and what? And the answer is y, the number y. And then we take y and we use g to produce the answer for R. Okay. So if we have an effective method of solving Q, we'd get an effective method of solving R because F and G are both polynomial time. Okay. So that's many one reduction. And then the classic paper for this is really Papanomitriou's paper from '94, where he defined the terminology and gave and really sort of categorized the standardly studied set of TFNP problems. Let's start off with just one example, and then I'll give some more, is the pigeonhole principle. So here the pigeonhole principle is we're given an input x and some description of an injective function mapping x to x minus 1. This looks very familiar to what we did earlier, but now it's a function. It's not just the graph of the function telling us, given x and y, whether f of x equals y. It's a method of going from the input x to get f of x. And the output is some a not equal to b, where either f of a isn't correctly in the range x minus 1, or f of a is equal to f of b, right, violating the injectivity. There always must exist some a comma b with this property because there is no one-to-one mapping from x to x minus 1. Once you find a and b, it's easy to check this condition because you just evaluate f of a and then evaluate f of b. So it matches the conditions for a TFNP problem. Traditionally, one specifies the function f in terms of a Boolean circuit. So we have an input to the circuit is the bits of x, and we're trying to compute f of a, say. The inputs to the circuit are the bits of a. The output, we have multiple output lines of the Boolean circuit, and that gives us the bits of f of a. Or we can do the so-called generic TFNP problems where we have an oracle specification of f, so we have black box access to f. In particular, the input size is polynomially bounded in x. We don't count the size of the oracle towards the size of the input. Or the circuit only has polynomial size. So the overall, if you think of the entire function as a set of ordered pairs, it's exponential size, but we have a polynomial time description of it in some way. Okay. And strictly speaking, for Papanomitriou, PPP is a set of TFNP problems that are many-one reducible to this problem pigeon. Okay. And he gave a big catalog of these things. So PPP I just described. It's the set of things. It's based on the principle there's no injective map from x to x minus 1. PPA, the polynomial parity argument, I guess it stands for. Any undirected graph with all node degrees less than or equal to 2, which has a vertex of degree 1, has another vertex of degree 1. So here the NP search problem is the following. I give you in some way, maybe a Boolean circuit describing it, a graph. I tell you that all nodes have degree less than or equal to 2. I also show you one particular node that has degree 1. And then we say there's some other node that has degree 1, and your job is to output it. Right? And we know this thing exists because if you start at a degree 1 thing, you follow the edge going out of it. If it goes to a degree 2 thing, you follow the other edge going out of it. You keep following the other edges out of degree 2 things until you hit another degree 1 thing, and then that's your solution. So there's at least one solution. Of course, there may be multiple solutions. PPAD is the directed version of PPA. You're given a directed graph. Every node has both in degree at most 1 and out degree at most 1. You're giving a vertex of total degree 1, so its in plus out degree is 1. And we have to find another degree 1, another total degree 1 vertex. Similarly, this is also a TFNP problem. And PPADS, this is S is for source, or sink, I'm not sure which, one of those two. If you have a directed graph with all its in and out degrees less than or equal to 1, just as in PPAD, if you also are given as input a source, then you have to find a sink. Okay. The previous problem didn't ask for necessarily a source from a sink from a source. It could have been another source, right? Okay. So these are some of the standard classes that he's done. And you can see these are all similar in scope to the pigeonhole principle.
On the previous slide?
Oops.
Oh, yeah,
Oh, this one. Oh, good.
So whether you use the function you specify by A or B changes the complexity class very much, right?
Whether you, wait.
Either as a Boolean circuit or an oracle.
Yes, it's a very different type of thing. So one of them, in the oracle setting, we can actually get unconditional separations between classes. In the Boolean circuit setting, we can't, because if P is equal to NP, all these things collapse to being in P. So you can't get any separations in the Boolean circuit setting unless you prove P not equal to NP.
In the oracle setting, you could unconditionally show it takes exponential time.
In the oracle setting, yes. In particular, you can show that all these 4 classes are distinct in the oracle setting. Paper by Beam, Cook, Edmonds, and Pagliazzo, Tassi, okay, that shows these are all separated. Baresh, Oppenheim, and Morioka, I think, somebody else also gave some more separations of this type. So there's a lot of separations that can be done in the oracle setting. These are all different classes. Okay.
Sam,
Yes?
why is this true? The PPA condition, why is that true?
Why is the PPA, okay, why is PPA total? Why, well, again, let me give you the argument again. Every node has degree at most 2. I started a node at degree 1. I follow the edge coming out of it. If I reach another node of degree 1, I'm done. Otherwise, I reach a node of degree 2. So I follow its other edge coming out. Again, I either reach a node of degree 1 and I stop, or I go to another, follow the other edge out. I just keep going. You can't go into a loop because that would give you something of degree 3 someplace. So you have to terminate at some other node of degree 1. You just follow the path starting at the given degree 1 node until you reach another degree 1 node. Now that could be exponentially long, of course, but you could ask for, because if there's a circuit describing the graph, there might be some shortcut that you could take to get the other node quicker. In the oracle setting, no, you can't do better. And likewise, PLS, which I already described, which here I just, a directed graph without degree at most 1 and a non-negative cost function which strictly decreases along directed edges has a sink, right? So rewrite PLS in that form. It's the same way of stating what I said before. And there's many more classes, but I was going to, these are maybe the most commonly studied ones, so I was going to stop here in his list of his, not the whole talk, but a list of Pop and Michio's classes. Okay, questions on this? There's a fair amount of study and a lot of recent activity in this area. I want to relate it back to bounded arithmetic, though. Any questions on this? And again, the point is these are classes intermediate between P versus NP. So we think NP problems are hard, and now we're looking at the fine structure of things between P and NP. Okay, so now, as I remarked earlier, the sigma B1 definable functions of bounded arithmetic give rise to TF-NP problems because all our theories are true. So if they prove that for all x there exists a y satisfying some property, then there really does. And so there's at least one. So, and since it's sigma B1 definable, we can make this be a TF-NP problem, or at least a projection of a TF-NP problem. I would say actually there's a pretty big gap in time before people made more progress on getting past T12. We had S12 had the sigma B1 definable functions were the polynomial time ones. T12, the sigma B1 definable functions were the projections of the PLS problems. And then it wasn't until 2007, the Krychek, Skelly, and Toppin came with colored PLS. This was a different, I guess I don't want to go into the definition of it, but just mention at least it's a Heerbrandized version of the PLS problem, which has a co-NP definable set of feasible solutions. Remember that F property that we had earlier, the F of XS. Instead of being polynomial time, it's now co-NP. And colored PLS is many one complete for the TF-NP problems of T22. So we actually get a characterization of the sigma B1 definable functions of T22. So again, we're looking, let me write that down. So we have if F is, I'll erase the part of that hard to get independence results for T22 and instead write F is sigma B1 definable by T22 of alpha, well, by T22 implies F is, well, F is a projection of a colored PLS problem. Okay, which I haven't fully described for you, but at any rate, it exists here. And I will end up with one final thing. And then there's a generalization of this to higher levels of Beckman and myself, where you deal with the Heerbrandized search problems for pi pk minus 1, well, for sigma, for tk2, let's put it that way. Okay. I'm going to be a little selective on what I cover here. A couple more problems that have been looked at a lot, and this is a little bit repetitive from my earlier lectures, but let's say it again here. Weak pigeonhole principle says there's no injective map from 2x to x. And I already described here, it's definable as a TFNP problem in T22. I already talked about that. The Ramsey theorem would give another TFNP problem, a graph G on X on a set of X many nodes, either as a clique or an independent set of size 1/2 log X. Right? This classic error dodge theorem about Ramsey's graphs. And Ramsey's theorem is provable as a TFNP problem in T32. Okay. Again, I stated this earlier, it's an open question, is it provable in T22? We don't know, right? But these are other natural sort of TFNP problems that come out of bounded arithmetic. Questions, comments? No, I'm going too fast. Well, we might end a few minutes early. Let me mention, there's a Herbrandized ordering principle that says any linear ordering, not necessarily respecting the usual less than or equal to, just a general partial order, but this linear partial order given by some binary predicate curly less than, can't have a total immediate predecessor function. You can't have a function that gives you the immediate predecessor in this relation because, of course, being an ordering, it has to have a least element. So some member doesn't have a predecessor. Okay? But because the ordering doesn't respect the usual less than or equal to, it's hard to do induction on it. It's hard to prove this fact. It actually turns out it's provable in T22, but okay, it's probably not many-one complete for the problems of this theory, unlike the colored PLS. Another very nice one, or even nicer, game induction. I had a hard time stating this, succinct one-word thing, but Neil is here. He can maybe improve on this. Is a winning strategy for a two-player K-round game. It's preserved under iterations of many-one reductions between games. This is Skelly and Toppin showed that this is many-one complete in general for TK2 by an embedding of induction into the game induction setting. Pavel and Neil proved some similar results for K-round max-min games and the Nash equilibrium principle as well. The Nash equilibrium principle is now known to be complete for PPAD, by the way. I didn't put that on earlier slides. But so a lot of these things, and okay, another principle here. It's a different kind of Nash equilibrium principle, right? So I said a related Nash equilibrium principle, right? It's not the usual Nash equilibrium principle. So going through here, there's a big line of work which I'm not going to cover because it's a little too complex, is local improvement principles. So K-round local improvement principle says you have an acyclic graph that you're updating labels in a consistent, well-founded way, can be done for K rounds. So this is a much more complicated thing to state, but again, you can get for TK2, say, you can show that this K-round local improvement principle is many-one complete for the TFNP problems that are, say, sigma b k defined, that are sigma b1 definable in TK2. And there's a whole host of similar results for U12 and V12, the p-space and exponential time algorithms, which I will not. There's rectangular versions and linear versions, and you change the number of rounds around, and all sorts of complete problems come out. But I wanted to instead end up with some stuff about Frege proof consistency, which I want to talk about Frege proof consistency itself as a total NP search problem. So here we've got a Frege proof P specified by an oracle. It could be specified by a Boolean circuit instead, but specified by an oracle. And the oracle tells us the ith symbol in the proof. And you want to show that this is not a valid Frege proof of a contradiction. So you've got this exponentially long, the first symbol is x of 0, second symbol is x of 1, long ways later, last symbol is x of a, and this is supposed to be a Frege proof, written out as a string of symbols. And the last thing is supposed to be, say x and not x, a contradiction. And all the intermediate results are supposed to be valid axioms or things inferred by modus ponens. And so the Frege consistency search problem takes a Frege proof specified by a second order object x, which gives oracle access to the symbols of the Frege proof, and a first order object x, which tells you the length of the Frege proof. And the output is supposed to be a set of places in the proof that shows X doesn't code a valid Frege proof, right? So the idea is, again, because it's an oracle, think if you're given this humongous proof. It's a big stack of things like this, and it says, you know, I'm a proof of a contradiction in Frege or something like that. You want to say, no, you're not. Well, it says, prove it. Well, okay, you have to find on page 1,000, it refers to a formula back on page 400, and that it's mistranscribed it or something like that, okay? It is a total search problem. Frege proofs can't prove a contradiction because... Okay, yes. So yeah, so it's total because or you could say it doesn't end with the statement X and not X, right? So you can't prove X and not X. That's not a tautology. So there has to be an error somewhere in the proof, assuming Frege systems are consistent. Okay. Right. I mean, that, again, if you're an ultra-finitist, you might worry that maybe exponentially long proofs can slip in a contradiction or something like that. Okay. But there's various things. Since the Frege proof is exponentially long, it can contain exponentially long formulas as well, right? Not just exponentially many formulas, but exponentially long formulas. But the number of places where you sort of bookmark the proof and say, hey, these places together show it's not a valid proof, should be finitely many places. So again, the mental picture is given a huge proof, and you're supposed to pick out here page 7 and page 11 and page 47 all contradict each other in some way, so it's not a valid proof, right? Okay. And so, so to do this, a little tricky because we want to express this, but basically to do this, we very carefully encode the proofs. So Frege proofs are encoded by fully parenthesized formulas. We use commas to separate the formulas. Each parenthesis has a pointer to its matching parenthesis, right? So each left parenthesis has a matching a pointer to the matching right one, and vice versa. Each comma at the end of a formula has a pointer to the previous formula. I guess you don't really need that, but also to pointers to the formulas used as hypotheses if it's inferred by an instance of modus ponens. Okay? And in this way, you can just literally identify a syntactic error in the proof. So it might be something like you say, one way to find an error would be to say that there's an instance, you know, somewhere in this proof there's supposed to be an instance of modus ponens, right? So someplace there's a formula A, formula B that says I'm inferred by modus ponens from A and A implies B. But then when you go to the trillionth symbol in B, it doesn't match the trillionth symbol in this copy of B. And so you just say this B is supposed to come from this, and its trillionth symbol is supposed to match the trillionth symbol of this B. It doesn't, you know, contradict the error in the proof, right? So with finite amount of information, even though the formulas are exponentially long, and you can't just verify directly that this formula A is that this formula is A, you can find a mistake by just showing the symbols don't match up. So a finite polynomial amount of information is enough to identify an error in the proof. Okay. So just to convince you, oh, we saw this already. Here's an example of proof of A implies A. So here's a proof of a contradiction. So it starts off with like the axiom A implies not A implies A. It works and gets A. And then we do the same thing again. We just interchange A and not A, and I write it here. And I get not A. And then from A and not A, I get a contradiction, which I wrote as the bottom. Okay? So there must be a syntactic error someplace in this proof. Okay. Where is it? Okay, there was a valid proof of A implies A. There was a probably invalid proof of a contradiction. Last time I did this, no one could find it. You might remember. You were in the talk.
I haven't read.
You haven't seen it before. I don't remember. Let's try that. Anyone see the error? Valid proof, invalid proof. Well, actually, so if you look at this line here, it's a little hard. There's so many A's, it's hard to see it, right? See, this is A implies B implies A, implies A implies B implies A implies A implies A implies A, right? Okay. This one here, I've just changed the B's to not A's, but I lost that last implies A on the top. So that earlier proof came up with an A implies A here, and I came with just an A here, right? Okay. So it's, you know, if you're a computer program, it's trivial to find these kind of errors. If you're a person, it's not very fun. Okay. Okay. So the theorem is then the Frege consistency search problem is many-one complete for U12 for the sigma B1 definable functions of U12. And you can likewise define the extended Frege consistency search problem. It's many-one complete for the TFN problems of V12. Okay. So, okay. All right. Thank you. Oh, I think we have time for discussion still, right? I ended way early. Oh, sorry. Okay. Okay.
Are there corresponding theorems that can be done all this latest theorem in size by interpolation?
Oh, so you want to do interpolation to get similar things about complete TFN? I mean, no one's done this. So interpolation, so you want to get TFNP problems via interpolation, or interpolation, I guess most of the uses of interpolation have been to show lower bounds on proof complexity. So we have interpolation to get separations, in propositional setting for getting lower bounds on resolution. Although we have other ways to do that. In the cutting planes, it's used there for lower bounds. In the natural proof setting, it's used to show conditional and unconditional lower bounds along with assumption of a pseudo-random number generator. So far, I would say there's Bonnet, Patasi, Raz, that it's hard to do interpolation for Frege unless certain types of integer factoring is easy. Right, so this is really used for a conditional lower bound. So if it's automatizable, it's a kind of interpolation, and you're saying that if you can automatize Frege proofs, then you can get Frege proofs. Then you get polynomial time algorithms for factoring Blum integers and so on. So these are.
There are some results of paper and also Picasso about interpolation against some kind of parity games, right?
Oh, interpolation for parity games. Maybe someone in the audience who actually wrote the paper should speak to that instead. Did you use interpolation in that paper? I don't remember that now.
Yes, what is the question?
Yeah, but I lost the question too.
Okay.
No, I mean it's parity question.
One thing they have in common is both things give you a way of getting some kind of machine that does something you can't do, but on the scale of it somehow different.
Mm-hmm.
Interpolation converts it directly into circuit. These things are more
Yeah. Yeah. I mean, one thing I would like to see people do, this has nothing to do with in interpolation, but these proofs, these last things about consistency statements give a very clean statement of TFNP problems for U12 and V12. There's two directions you could extend that. One is, of course, these are maybe too logical. There might be a more combinatorial way to talk about these things. The local improvement principles do that, but I'd like to see cleaner, simpler versions of the local improvement statements that are combinatorial things. And a lot of, not to say bad things about the work, but I think there could still be even better, right? Could challenge people in the audience who've done this work to do even better. The other direction is, and again, I think this is eminently feasible and probably even follows from some current existing work, is to give clean versions of these things for TK2 theories. And actually, I think maybe this is already done at this point, but I'm not sure anyone wants to announce it yet, right? Okay, but I think there could be much cleaner connections between bounded arithmetic and propositional logic even than we currently have. And it would be good to see that stuff worked out. Okay. And ultimately, we should prove P not equal NP, right? But I'd be happy showing right now that bounded arithmetic doesn't prove P not equal NP. Right. Either that or show bounded arithmetic does prove P equal NP, or but it's probably not going to happen.
You mentioned several times the thing extracting natural proofs from some theory. So I didn't understand what you exactly meant.
Oh, okay. So the way this works is Razborov shows that if T12 proves certain types of circuit lower bounds, okay, then from this T12 proof you can extract a so-called natural property against circuits, against functions having circuits of polynomial size. So what this natural property means is it's a property that looks at the truth table of the function and it finds evidence that it doesn't have a small circuit. And
so this means whatever lower bound you can prove in that theory, this gives you a natural proof.
well, you said whatever lower bound. I'm not quite sure what you're including that, but certainly for these circuit lower bounds, for directly circuit lower bounds, yes. So these are circuit lower bounds for predicates defined by delta knot properties, right? So you have a delta knot property, there's a circuit that computes it. If you get a lower bound, then you can get a natural proof out of that. And depending on what theory you're working in, if it's a very weak theory, then you just get an unconditional proof that you can't make this proof. Otherwise, you get these conditional proofs that say that if there's no pseudo-random number generator of a certain type, then you can't get a proof in the bound arithmetic theory of these superpolynomial circuit lower bounds. Right.
Well, there seems to be no more questions, so thank you very much for a great tutorial.
Thank you.